All right, so what I'd like to talk about now is where blackbody radiation equations come from that you find in common heat transfer textbooks. To do this, what I'm going to do is I'm going to draw a box that's meant to represent radiation inside an enclosure. This enclosure is meant to be at statistically thermodynamically equilibrium states. So this is my box, and I'm going to treat this as the particle in a box type solution for photons, which behave very similarly to phonons. So I have a bunch of standing states of photons inside this box. And what I'm going to do is imagine that I have a surface element that's sitting somewhere in the interior of the box, and I want to calculate how much energy actually passes through that little square. So this is my surface element, and I'm imagining that I have photons that are essentially at thermal equilibrium moving everywhere throughout the box at a well-defined temperature T. Then what I'm going to do is actually write out the energy density inside the box. So that would be given by the solution to a quantum oscillator inside of a box. And so that would be n times h bar omega would be the energy. And then I'll divide that by the volume. So that'll be the energy per volume. But the value of n is not just any quantum state. It'll be the equilibrium statistically thermodynamic set of states from the Bose-Einstein distribution. So I'll write that out explicitly later, but for now I'll just call it the average value of n. Now, the intensity of any mode will represent how much energy per unit area is being carried by that mode, and that'll just be the energy density times the speed at which it travels, which is the group velocity. Let's check the units here. So energy density is joules per meter cubed, and speed is meters per second. So that gives watts per meter squared if you check it out. Now for a photon, the group velocity is just the speed of light. So d omega dk is just the speed of light. C, which is at least in a vacuum or in air, is a well-known constant. All right, now what I'm going to do is actually count how much energy passes through my little surface element that I've drawn in the center of this box. And in particular, I'm really only interested in how much energy goes through in one direction, because I know the net amount of heat flux going through the element is zero. But if I'm looking at it from a one-sided point of view, so let me call the element of area dA with unit normal n. Now the intensity of light doesn't necessarily go directly through the element, right? It could come through at an oblique angle. And so what I'm really interested in is the amount of energy projected onto the amount of area. So that'd be I dot n. And so the intensity, or the magnitude of the intensity, is just the energy density times Vg. And then I'm going to dot that on the unit normal, which really just gives me the speed of light times the cosine of the angle between the intensity and the unit normal. Then I would just point out that, so I'm going to have to add up all of this power going through the element for all of the different possible directions of light going through the element and all the possible polarizations. So let me just point out that there are actually two polarizations for each type of photon or light that can go through the element. One which has sort of electromagnetic waves that are, let me call them in plane, and another one that's perpendicular to that would be sort of the up-down direction. I mean, it doesn't have to be in plane and through plane, but the key thing is that there are two independent polarizations, and all photons are transverse. All right, now we need to start the process of actually adding up all of the contributions from all of the different possible photons that can go through our little element. And so what I'll do is I'll use the fact that all directions of propagation are equally likely for photons. So in order to calculate the heat flux going through the thing, or the heat divided by what the area of my element is, I'll take 2, which is the number of modes, types of polarizations that can go through, and then I'll integrate over all of the possible wave numbers that can go through. So for each wave number, I'll take the energy density times the speed of light projected, so that's the cosine phi, projected onto the unit normal, and then I'll integrate that over all possible k vectors. And the factor of 2 pi over L cubed is just the essentially the density of states, or the discreteness in k space. Then it's always easier when you see these kind of integrals to do them in spherical coordinates, especially since we basically only need to integrate over one side of a sphere. So what I'm going to do is, instead of doing kx, ky, kz, I'll just do it in terms of k, and then I'll think about the angles. Let me pull out some prefactors that come from the energy density, and then I'll pull things out in terms of spherical coordinates. So I'll pull out you integrate theta from 0 to 2 pi, integrate phi from 0 to pi over 2, which means just 1/2 of a sphere, times the cosine phi, which comes from taking the dot product. And then there's a factor of k squared times sine phi that comes just from the conversion to polar coordinates. And then there's an extra factor of k that came from the frequency being equal to the speed of light times k, which I've highlighted up here. And then we'll divide that all by the Bose-Einstein, or multiply by the Bose-Einstein distribution, and carry out that integral. All right, in order to actually carry out those integrals, especially the k integral, what I'm going to do is make a change of variable from k to another variable, which is the whatever that thing is that's inside the exponent of the exponential. So if I make a change of variable from k to x, and where x is defined as h bar c over kbt, so I have it written here in parentheses. Then I'll actually be able to carry out that integral using either integral tables or numerical integration. The integral of x to the third over e to the x minus 1 from 0 to infinity, it can be calculated, and it just turns out to be pi times, 4 over 15. And so, if you use that fact, you can actually evaluate the integral. So if you combine all that together, you can calculate a relationship between the heat flux through the element and the temperature of the box. And of course, what you end up finding is that the heat flux through our little element turns out to go as t to the 4th power times some constant known as the Stefan-Boltzmann constant. So what we've actually found here is the Stefan-Boltzmann law for radiation that is commonly shown in a first course in heat transfer. So if you were curious about where it comes from, that's where it comes from. It's actually sort of a universal law that really just has to do with how photons populate themselves in an enclosure.